Welcome to this video series on exponential and logarithmic equations. This is going to be the first video in this series, and hopefully by the end of this lesson, you will be able to work with index laws. You might be wondering, why is it called exponential and logarithmic equations, and we're dealing with index laws? Excellent question. Let me have a quick chat about that. All right, exponential and logarithmic equations, they're actually quite tricky, and in order to really work with them efficiently, we need to make sure we understand quite a number of fundamental concepts. And as soon as we're all over these concepts, such as index laws, we'll be fine working with exponential and logarithmic equations. So bear with me. Let's have a look at index laws today. In the next video, I'm going to have a look at the log laws, and then from there, we can start building up working with exponential and logarithmic equations. All right, so plan for today, let's get the index laws down. All right, let's have a look at index laws. If a number is represented in index form, it doesn't look like the normal way that we know our numbers. If we know our numbers, all right, that's 9. But we can also represent 9 in index form. That would look 3 to the power of 2. Let's quickly talk about a few definitions here. This little number here at the top, that's called our index, okay? That's our index, or there are quite a few names for this number. You can call it the power, you can call it the exponent, or the logarithm. So there are quite a few names for this. Then we have the number here, which is called the base. All right, so just get a few definitions out of the way so that we know what we're really talking about. So now what does that actually do? What does that mean? If you write something like 3 to the power of 2, you have your index 2 and your base 3. The index tells you how many times you multiply the base by itself, okay? It's not 2 times 3. I've seen students do this, which is quite intuitive. 2, is the number at the top, 3 is at the bottom, so 2 times 3, that would give us 6, but that's incorrect. What we need to do is we multiply the number by itself 2 times, okay? This is why it's raised to the power of 2. 3 times 3 gives us 9. We started with our 9, put it into index form, 3 to the power of 2, and now we brought it back to just our number 9. All right, I hope that makes sense. So from here, what we can move on to, instead of writing with numbers, when we look at laws, we always want to represent this situation here with variables. There we can say a to the power of x. A just tells us our base can be any number. That's still our base. In our example up here, it was 3. And the little number at the top is our exponent, or index, or our power. And that also tells us this can be any number. And so if we think about index form, this is what we're talking about. All right. I hope that makes sense to really get the basics down. Let's have a look at the laws that are set. We're going to work our way through today. All right, let's look at law number 1. If you have something like a to the power of x, just like we said, a can be any number, which is our base. Our little exponent here is x, which could be any number too. Then we want to multiply this with another number in index form, a to the power of y. How can we simplify this? How can we, instead of 2 terms, make this into 1 term? Let me show you straight up the law, what happens. So if we have a multiplication between these two, we just add our 2 exponents together. How does that work? Let me give you an example. Let's say we have 3 to the power of 3 times 3 to the power of 2. We just say, all right, if we just follow our law here, x plus y, so 3 plus 2, that just gives us 3 to the power of 5. Why does that work? Let's quickly have a look at that. Let's say we have this one here, which is 3 times 3 times 3. Then we bring our multiplication sign down. Let me redraw this arrow here a little bit clearer. We bring our multiplication sign down, put this multiplication sign here, and then we bring our 3 to the power of 2 down, which is 3 times 3. All right, let's have a look. So that gives us then, oh, nice, look at this. 1, 2, 3, 4, 5 threes, and they're all multiplied with each other, so 3 to the power of 5. Nice. So I hope that makes sense where this is coming from. If you multiply This is our law. If you multiply two terms to index form terms, you just add the exponents together. Law number one, let me write a little one here, done. Let's have a look. Let's move to the side here a little bit that we can start with law number two. All right, I hope you can see that. And in the first example, we multiplied these two terms together. In the second example I'm going to give you, we want to deal with division. So in this case, we divide. So that's a big difference here. And maybe, just maybe, intuitively, you can say, all right, in the first example, we just added our two exponents together. What do you think we got to do here? Correct. We subtract, all right? So we subtract our two indexes or exponents from each other. Why does that work? Let me give you an example again. Let's say we work with 3 to the power of 3 again. We divide it by 3 to the power of 2. And that, just following our law, should give us 3 to the power of 1. Because we say 3 minus, let me write this out again. Let's make sure that we're all good with this. 3 minus 2 gives us 3 to the power of 1. All right, why does that work? Let's have a look. Let's write this one first. 3 times 3 times 3. Then we want to deal with our division sign. Let's write this as a fraction. This is just exactly the same division. Numerator, the number at the top, divided by the number at the bottom, our denominator. And that's 3 times 3. That's this term here. All right, so now let's have a look. Why does this now suddenly become 3 to the power of 1? That's funny. Let me show you this. What we can do here, we stick with white. What we can do here, we can cancel out 3 at the top and 3 at the bottom. They cancel each other out. You can do this when you multiply your terms at the top and terms at the bottom. You can cancel numbers that are the same out. Why can you cancel them out? Excellent question. Let's have a quick look. If you cancel out something like 3 over 3, that can be simplified, and you can rewrite this as 3 over 3 as 1. Any number divided by itself just becomes 1. And if you imagine these two terms here, 3 divided by 3, this is 1, and you multiply it by 3, that just gives you 1 times 3 times 3. At the bottom, 1 times 3. What is left here? All right, 3 times 3 is 9. 3. All right, so see, it's exactly the same numbers. 3. And this is 3 times 3, so that's 9. So you don't need to write this. This is why you can cancel that out. So I hope that makes sense for our second index laws. So if you divide, you just need to subtract your exponents. Nice. Next law number 2, done. From the second index law, I really like to jump straight into number 3. Give them the numbers 1, 2, 3. Some people might call them a little bit in a different way. Doesn't matter too much. I call that index law number 3, and this is any number to the power of 0 will always give you 1. All right, I'll give you this law straight up. Let's think about it. Now that we just talked about when we divide our index form laws, we can follow up with this. Let me give you this example. A to the power of 3 divided by a to the power of 3. All right, we just learned that law, and we can simplify this as a to the power of 3 minus a to the power of 3. All right, so we can simplify that to that. That gives us exactly a to the power of 3 minus 3 is 0. So that should give us 1. Why does that give us 1? Let's write this as our fraction again. 3 times a divided by 4a times a, all multiplied with each other. That gives us 1. That gives us 1. That gives us 1. Like I just said earlier, any number divided by itself gives us 1. So that would give us 1 times 1 times 1 at the top, 1 times 1 times 1 at the bottom, and 1 times 1 times 1 is always 1. All right, I hope that makes sense, and you can see where this law comes from and how that can be proven. All right, another one smashed out. We're going through them beautifully. Let's have a look at number 4. Let's call this number 4. Let's have a quick look. If you have an expression, so your base is raised to a negative power. So for example, a to the power of minus x. You can rewrite this as a positive index. So you want your x to be positive. How do we rewrite this? We just rewrite this as 1 over a to the power of x, okay? A to the power of x. And what we really achieved here is our exponent or our index is not negative anymore, okay? This is much nicer to work with. One thing we need to keep in mind, a cannot be 0. Why not? Because a is in the denominator and you cannot do any division by 0. So a cannot be 0. Nice. Let me show you straight up another example. I'll just write them down here next to each other. Number 5. In this case, we have our base raised to a fraction. So a to the power of 1 over x. How can you rewrite this? How can you rewrite this to deal with this expression in a different way, in an easier way to solve your problem? All right, let's have a quick look. You can rewrite this as you taking the square root out of the number in the denominator. That sounds really, really difficult. The only thing you need to remember is the number in the denominator of your expression becomes the number that you take the square root with. So in this case, square root, the x square root of a, so the number, our base, okay? Here again, x in this case cannot be 0, just like we said in our first example. X cannot be 0 because x is in the denominator and x therefore cannot be 0. Let me go straight away to the 6th one. When we have something like that, I'm just building up, they get a little bit more and more tricky. Let's have a look at this one. If you have something a, our base, raised to a power of x divided by y. Same idea. We want to be able to deal with this in a different way. And so we're still working with this root idea here. So in our example number 5, we had x in the denominator of the little fraction in the exponent or in the index. We made this the xth root. In this case, y is in the denominator, so we need to make sure that y is now the yth root we take. And what do we do with the little number in our numerator? So at the top here, we just raise the base a to the power of this little number that's in the numerator. So we can rewrite this as that. Or from here, we can then also say we take this x, that stays all the same. We take the exponent of the base here to the outside of our yth fraction, and we rewrite it like that. All right. I'm just going through these examples now. You don't need to worry too much if there's something unclear. We're doing a few examples straight after I showed you all of the laws, okay? So here, in this case, you see that y is in the denominator up here. So this is y. Y again cannot be 0. All right. And then I want to show you 2, let's call them 7 and 8. 2 last laws. They're not necessarily laws in itself, but 2 properties we can use. If we have something in fractions, such as a times b, and that's raised to a power, we can distribute this index to each term in the bracket. What do we achieve with that? We can get rid of the brackets. Similarly, if we have a fraction in brackets here, and this is raised to a power of x, again, we can nicely distribute this exponent. And what do we achieve by that? We get rid of the brackets. That's a nice thing. Again, in our example here, b is in the denominator. B cannot be 0. Nice. Smashed all our laws out. Let's have a quick zoom out. Look at this. So we covered all of our laws. We talked about them all. Let me now give you some examples. I'll zoom down here. And let's have a look that we change maybe the color. It's time for a bit of a change. What are we thinking? Let's keep on working with blue. I don't like red. Let's have a look at some examples here that I can hopefully make it a little bit clearer for you how we use these laws and how we then apply them all at the same time. All right, let's look at an example. All right. Let's have a look at an example. All right, if we have something like 64, and this is raised to a negative index of 3 minus 2 over 3. Oof, that looks quite tricky straight up, but it's not that wild. All right, so let's have a look and work our way through it step by step. If you have a negative index, it's always nice to get rid of the negative index. So we want to get rid of this minus in front of the index of 2 over 3. Remember, one of our laws was if we rewrite this as 64 to the power 1 over 64 to the power of 2 over 3, then you can get rid of your negative index. Nice. First thing done. That improved it. Now, what's the next step? Also, I showed you this little law, remember, where we said a to the power of x over y. We could rewrite this as taking the y root of a to the power of x. All right. So now let's rewrite this term in our denominator. So here, this one here, using this law. All right. What do we get from that? That becomes 1 over 64 is our base. That is, we take the third root, so the cube root, out of this, and then we need to have a look what was in our numerator. That was 2. And now we can simplify this. And now from here we can move on and further simplify this. What does the cube root actually mean here? Let me move this a little bit over here. From here, what does the cube root mean? We still have 1 over the cube root of 64. So the cube root asked which number do I need to multiply by itself 3 times to make 64. So if we think about this idea, let me quickly go to this little side note here. Cube root of 64 ask which number do I need to multiply by itself to make 64? Let's say 2 times 2 times 2. What's that? 2 times 2 is 4. 2 times 4 is 8. So no, that's not what we're after. 3 times 3 times 3, 27. 3 times 3 is 9. 3 times 9, 9, 18, 27. No. 4 times 4 is 16. 4 times 16 is 40. 24, 64. Beautiful. That's what we're after. So you can simplify this one to 4. All right, so we have 4 in our denominator up here. Let me quickly get rid of all of this. I don't want to have too much writing on here. I just wanted to clarify that. If you're not sure, go back and watch this one more time just to make sure that you're all good with the idea of taking the cube root of 64. So now we simplified this to the cube root of 64 was simplified to 4. And then we need to raise it. Oh, this is still to the power of 2. And 4 times 4 just gives us 1 over 16. Excellent. Nice. First example done. Hope that makes sense. And you could see how you use one index law after another, and then you work your way slowly and deliberately through all of the tricky parts to simplify it further and further. All right, I'm not going to write the whole word example again because it was pretty painful last time. Let's have a look at this. I'm just writing x2. All right, let me give you another example. Let's have a look at this. If we have 32, and this is raised to a negative index of 0.4. Okay, similar problem to what we just dealt with. But here, we have a decimal in the index, so we need to deal with it a little bit differently. I might give you a second if you want to pause the video after I've seen the first example. I think you're pretty well equipped to have a go at this. So if you want to pause the video, just pause it now. Awesome. For everyone who had a crack, good on you. I'm going to show you how I would deal with this thing again. First thing that I would want to do, I want to get rid of this negative index. So how do I write it? 1 over 32 to the power of 0.4. So that helps me get rid of this negative index. Beautiful. Next step. I want to get rid of this decimal here, this 0.4. That's really not really nice. We know that we want to, when we convert decimals into another form, there are certain ways. There's this conversion of decimals to percentage and conversion decimal to fractions. And we've been always working with fractions here, so it would be nice to have 0.4 written as a decimal. Remember, if you want to convert a decimal into a fraction, you just check 0.4. So it's in the 10th position after the decimal point. So we need to write 4 over 10. Just another example. If you, for example, has 43, that's in the 100th position. So that would be 43 over 100. All right. That's just a little side note. So what we were really after here was 0.4 written as a fraction is 4 over 10. All right. 4 over 10. Nice. 4 over 10, that looks much more familiar to what we've been working with the whole time. Let's keep on simplifying this. We can rewrite this as 1 over 32 to the power of 4 over 10 can be simplified to 2 over 5. You divide both 4 and 10 by 2. And here, after that, we continue doing our funny little taking the root business. So that's 1 over, remember, the number in our denominator here becomes which root we're taking. So we take the 5th root out of 32. And this is all squared because 2 is this little number in our exponent, in our numerator. Okay. Again, here we want to have the 5th root out of 32. And I hope you can see that if you multiply 2 times 2 times, not 3, 2 times 2 times 2. This is 1, 2, 3, 4, 5. That will give you 4. That will give you 8. That will give you 16. And that will give you 32. So that will give you 2 squared. 2 squared can be simplified to 1 over 4. So starting off with this problem here of 30 raised to this negative decimal index of minus 0.4, we can simplify this to 1 over 4. Awesome. I think these were 2 really good examples. I hope they made sense. Let me follow up with one last example number 3, just to give you something a little bit different. And then I think we made a really good start on our index laws. All right, let's have a look at something like this. 3. So in the last example, x raised to a negative index of minus 2 minus 3 over x minus 2. All right, that looks a little bit different, but I do think, having had a look at all of our index laws, we're well equipped to have a go at this. All right, if you want to try, pause the video now. Awesome. Well done for everyone who gave it a go. Let's have a look how we can address this problem. Remember, first thing, we want to get rid of our negative indices. So we're writing the first term as 1 over x to the power of 2 minus. And here we see that x to the power of minus 2 has a negative index. So we can rewrite this as 1 over x to the power of minus 2. Sorry, It's not over anymore because this whole term is in the denominator. And what do we really achieve with this? The x squared goes into your numerator. So that leaves us with 1 over x squared minus, we had our 3 here, that was 3, yep, we had our 3 here, so that gives us minus 3x squared. So like we always do, first step, get rid of our negative indices. After we've done that, we are left with this expression. All right. Next step is we have two terms, and one of them is this funny looking fraction here over x squared, and the other one is 3x squared. All right. We want to find the common denominator, and here the common denominator, so the number at the bottom, we can rewrite the second one as over 1. We want both of them to be over the same number. All right. So let's have a look. How do we do this? We would multiply this, the right-hand side, with x squared. Okay. So what does that give us? On the left side, 1 over x squared stays the same. And on the right side, that would give us 3x to the power of 2 over x squared. All right, if we multiply this term with x squared and we multiply this term with x squared, that will give us 3x to the power of 2 over x squared. From here, now that we have our fraction, we're doing this subtraction of fractions over the same denominator, we can further simplify that and combine this into one fraction, and that would give us 1 minus 3 over 3x to the power of 4 over x squared. You might not feel like we really achieved much, but we certainly simplified this whole expression and made it into one term, and this is what we were after. All right, thank you very much for having a look at this first video on this series. So for now, I think we have made a really good start on the index laws. In the next video, we're going to have a look at our log laws, and then we're not far off from really jumping into exponential and logarithmic equations. Thank you very much.